When wiring neutral grounding resistors, or NGRs, for high-voltage generator systems, several key considerations must be taken into account to ensure safety and proper operation. Firstly, the conductor connecting the NGR to the neutral point of the generator must be fully insulated for the full system voltage. In this case, that's 5000 volts. Secondly, National Electrical Code Section 250.36 allows the conductor to be run in its own raceway for systems over 1000 volts. This provides an additional layer of protection. Thirdly, you can run the grounding electrode conductor, or GEC, to the grounding connection point in the paralleling gear. All grounding connections can be made at that point. Fourthly, an insulated conductor, either rated for 600 volts or 5000 volts insulation level, needs to be run in a conduit from the NGR to the neutral point of the generator. This conductor can continue through the conduit to the generator set. Fifthly, run the 5000 volt circuit conductors from the paralleling gear to each generator without an equipment grounding conductor, or EG. An equipment grounding conductor would effectively shunt the NGR, rendering it ineffective. Sixthly, it is permissible to run two conductors to the NGR in the same conduit. One conductor runs from the equipment ground bus to the resistor. The second conductor runs back to the gear to carry any residual current. It is highly recommended to consult with experienced engineers and electricians who possess in-depth knowledge of high-voltage systems to ensure proper design and installation. The importance of adhering to the latest version of the National Electrical Code, also known as NEC, cannot be overstated. It is equally important to consult with local authorities to ascertain any additional requirements or interpretations that may be specific to your jurisdiction. The NGR serves a critical function in limiting ground fault current, thereby protecting equipment and personnel from potential damage or injury. The selection of the appropriate NGR resistance value is paramount. This value is typically determined by a qualified engineer, taking into account the system voltage, generator size, and desired ground fault current level. A lower resistance value will result in a higher ground fault current, while a higher resistance value will limit the ground fault current but may also reduce the sensitivity of ground fault detection. The NGR must be properly sized to dissipate the heat generated during a ground fault event. The manufacturer's specifications should be consulted to ensure that the NGR is capable of handling the anticipated fault current and duration. The NGR should be installed in a location that is readily accessible for inspection and maintenance. It should also be protected from environmental factors such as moisture and extreme temperatures. The conductors used to connect the NGR to the generator neutral and ground bus must be sized appropriately to carry the anticipated fault current. The conductor insulation must be rated for the system voltage. The raceway used to enclose the NGR conductors must be properly grounded to provide a low impedance path for fault current. The grounding electrode conductor, or GEC, must be sized and installed in accordance with NEC requirements. The GEC connects the grounding system to the earth, providing a path for fault current to return to the source. The paralleling gear plays a central role in the operation of multiple generators in parallel. It provides the necessary control and protection functions to ensure that the generators operate safely and efficiently. The paralleling gear typically includes synchronizing equipment, protective relays, and circuit breakers. Synchronizing equipment ensures that the generators are operating at the same voltage, frequency, and phase angle before they are connected in parallel. Protective relays monitor the generator output and trip the circuit breakers in the event of a fault. Circuit breakers provide overcurrent protection for the generators and the paralleling gear. The neutral grounding resistor, or NGR, is connected to the neutral point of each generator through the paralleling gear. The NGR limits the ground fault current, thereby protecting the generators and the paralleling gear from damage. The paralleling gear must be properly grounded to provide a low impedance path for fault current. The grounding electrode conductor, or GEC, must be sized and installed in accordance with NEC requirements. The GEC connects the grounding system to the earth, providing a path for fault current to return to the source. When installing the neutral grounding resistor, or NGR, it is important to follow the manufacturer's instructions carefully. The NGR should be mounted securely in a well-ventilated location. The conductors connecting the NGR to the generator neutral and ground bus must be properly terminated and tightened. The grounding electrode conductor, or GEC, must be connected to a suitable grounding electrode system. After the installation is complete, the NGR should be tested to ensure that it is functioning properly. The resistance of the NGR should be measured to verify that it is within the specified range. The ground fault protection system should be tested to ensure that it is operating correctly. Regular maintenance should be performed on the NGR to ensure that it continues to function properly. The NGR should be inspected periodically for signs of damage or corrosion. The connections should be checked to ensure that they are tight and secure. The grounding electrode conductor, or GEC, should be inspected for signs of corrosion or damage. If any problems are found, they should be corrected promptly. In addition to the NEC requirements, there may be local codes or regulations that apply to the installation of neutral grounding resistors. It is important to check with the local authorities to ensure that the installation complies with all applicable requirements. The proper installation and maintenance of neutral grounding resistors is essential for the safe and reliable operation of high-voltage generator systems. By following the recommendations outlined in this discussion and consulting with qualified professionals, you can help to ensure that your generator system is properly protected from ground faults. In summary, when dealing with neutral grounding resistors in high-voltage generator systems, always prioritize safety, adhere to the latest NEC guidelines, and seek expert advice. Correct conductor rating, raceway installation, and grounding practices are crucial for optimal system performance and protection. Always use a conductor that is rated for the system voltage. Never use an equipment grounding conductor from the generator to the gear if there is a neutral grounding resistor in the circuit. This will defeat the purpose of the resistor. Always run the neutral grounding conductor in its own conduit. Always bond the neutral grounding resistor enclosure to ground. Always torque all connections. Always verify the resistance value of the resistor after installation. Always perform regular maintenance on the resistor and its connections. Always keep records of all inspections and maintenance. Always consult with experienced engineers and electricians. Remember that working with high voltage systems can be dangerous. Always take the necessary precautions to protect yourself and others from electrical shock. Wear appropriate personal protective equipment, such as gloves and safety glasses. To energize and lock out the equipment before working on it. Follow all safety procedures. By following these guidelines, you can help to ensure the safe and reliable operation of your high-voltage generator system. The neutral grounding resistor, or NGR, is a critical component in protecting electrical systems from damage caused by ground faults. A ground fault occurs when an unintended connection is made between a live conductor and ground. This can happen due to insulation failure, equipment malfunction, or accidental contact. When a ground fault occurs in a solidly grounded system, the fault current can be very high, potentially causing severe damage to equipment and posing a safety hazard to personnel. The NGR limits the magnitude of the ground fault current, reducing the risk of damage and injury. The NGR is typically a resistor connected between the neutral point of a transformer or generator and ground. The resistance value of the NGR is chosen to limit the ground fault current to a safe level. The resistance value is typically chosen based on the system voltage, the size of the transformer or generator, and the desired level of ground fault protection. The selection of the appropriate NGR resistance value is a critical design consideration. A lower resistance value will result in a higher ground fault current, while a higher resistance value will limit the ground fault current but may also reduce the sensitivity of ground fault detection. There are several factors to consider when selecting the NGR resistance value. These factors include the system voltage, the size of the transformer or generator, the desired level of ground fault protection, and the sensitivity of the ground fault detection system. The system voltage is a primary factor in determining the NGR resistance value. Higher system voltages require higher resistance values to limit the ground fault current to a safe level. The size of the transformer or generator also affects the NGR resistance value. Larger transformers and generators can supply more fault current, so higher resistance values are needed to limit the fault current to a safe level. The desired level of ground fault protection is another important consideration. If a high level of ground fault protection is desired, a low resistance value can be used. However, a lower resistance value will also result in a higher ground fault current, which may cause more damage to equipment. The sensitivity of the ground fault detection system is also a factor to consider. If the ground fault detection system is not very sensitive, a lower resistance value may be needed to ensure that ground faults are detected quickly and reliably. Once the NGR resistance value has been selected, the NGR must be properly sized to dissipate the heat generated during a ground fault event. The manufacturer's specifications should be consulted to ensure that the NGR is capable of handling the anticipated fault current and duration. The NGR should be installed in a location that is readily accessible for inspection and maintenance. It should also be protected from environmental factors such as moisture and extreme temperatures. The conductors used to connect the NGR to the generator neutral and ground bus must be sized appropriately to carry the anticipated fault current. The conductor insulation must be rated for the system voltage. The raceway used to enclose the NGR conductors must be properly grounded to provide a low impedance path for fault current. The grounding electrode conductor, or GEC, must be sized and installed in accordance with NEC requirements. The GEC connects the grounding system to the earth, providing a path for fault current to return to the source. The neutral grounding resistor, or NGR, is an important component in protecting electrical systems from damage caused by ground faults. By limiting the magnitude of the ground fault current, the NGR reduces the risk of damage to equipment and injury to personnel. A proper selection, installation, and maintenance of NGR are essential for ensuring the safe and reliable operation of electrical systems.